Now we want to come to a general method which can be used in discrete memberless networks. You will see that we already applied in principle for the broadcast channel or for the multi-access channel this method. But let us look at some very general system like it's here in this picture. So you see that we have a discrete memberless network channel here. And through this channel, they are connected terminal 2, terminal 1, terminal 3, and terminal 4. And it's allowed for each terminal to have a source which gives it a message, but it could also make an estimate of a message of another terminal. So in this picture, you see terminal 1 gets some message W1, and he wants to estimate the message of terminal 2. Terminal 2 gets some message W2 and some message W3. Terminal 4 want to estimate the message W1. It's a fourth estimate of W1. Terminal 3 want to estimate also W1, W2, and W3. So each terminal could have an input of a source and want to get an output, and it is connected to a channel with the terminal from which it wants to have an estimate of its message. So what you can do is terminal 1 can send a message x1 to the n and receive a message y1 to the n. Terminal 2 can send a message x2 to the n and can receive a message y2 to the n. And that's a general true for all messages. Here, the sending is possible for terminal 3, but it's not necessary because it doesn't receive any message from a source. And this construct is called a discrete memberless network. And you see our broadcast channel and our MAC, if we use the encoders and the decoders as terminals, are of this kind of channel. So, and what did we do? So what we want to get now is a general method to get an upper bound for the capacity region. The idea, therefore, is to, first we come to more properties of this network. We must have that our theorem holds, it must be synchronous. That means we have a clock which always synchronizes each thing. So at every step, x1 is xi is sent and yi is received. So you see here xti and yti are received or sent at clock tick i-1. That's also true for our interference channel. And of course, also for the other channels, there we don't need a clock because only one terminal is sending really. So it's also important that the messages are statistical independent. So there are m statistical independent messages. So each message is statistically independent, each WM. That's also important. And MT is a set of indexes of the messages of terminal T. And then we have this output here, and we have the function which decides yti on x1, x2, xti, and zi. This is the principle what we want to have for a discrete memberless network. And the idea is somehow to estimate or to give now an upper bound that we partitioning the set of terminals into two sets, S and S tilde. And this pair S and S tilde we call a cut. And we say that the cut S and S tilde separates the message WM and its estimate WM hat of T if WM originates at a terminal in the set S, and T, where the estimate should be done, is in the complement in the S bar here. And then that was in principle, if you remember what we did for the broadcast channel, that was in principle how we get all these estimates. We just look at one encoder, for example, what rate he has, what rate we want to estimate the rate for him, and we look at the rest, for example, just to get an estimate for R1. And the same we did for R2, and then we did it for R1 plus R2. So that's somehow the method to use cuts. And the cut theorem says then that the capacity region is then a subset of the union of all Qxi x1 to xt and the cut over all S, which are subset under T, where R is the total rate, which is defined before. So you see it here. And this we want to apply now to our thing. So I already told you that we did this already for the broadcast channel. For example, the broadcast channel, you can look at it as it is a discrete memberless network with 1, 2, 3 terminals. And here is the channel. Terminal 1 receives 3 messages and just send this sequence here, it's X3. And the broadcast channel puts out Y1 and Y2 here. And terminal 1 want to have an estimate of M1 and M0 of the COM and the dedicated message, and the same is true for terminal 2. And here you see the cuts which we considered. So first we consider this cut here, we consider somehow X and the rest, and then we consider this cut here, and we consider this cut here. So we considered three cuts in principle, and then we have here, this gives you an estimate of R2, this gives you an estimate of R1, and this cut gives you an estimate of R1 plus R2. And that's exactly how we did it all. And if we have R0 also, then we get this estimate R0 also additionally. The same is for the MAC. The MAC you can see also as a discrete memberless network. So you have terminal 1, terminal 2, and terminal 3. And now you see the different goals here. Now terminal 1 and terminal 2 receive a message from a source and send a sequence here. And terminal 3 want to get to estimate. And what did we do there? We make a cut here to get, and we make a cut here to get an estimate of rate 1 and R2. And then we make a cut here to estimate R1 plus R2. So we leave out here this COM message as you recognized. So we do it in the Alswede style in this way. And now we can do it, and it's a little bit more complicated also for the interference channel. For the interference channel, we must have to do this cuts here. So you see it here, this is cut 1, where we also only have the 1 inside. This is cut 2, where we only have terminal 2 inside. Then we have a cut where we have terminal 1 and 2 inside. Then terminal 1 and 4, 2 and 3, 1, 2 and 4, 1, 2 and 3. And if you check now, if it's always true, so terminal 1 get some message M1 here. And of course, in the rest part, there's an estimate of this message. Same is true for terminal 2. Then if we took these two together, then of course the same is true. Then the rest want to have an estimate here. If you took 1 and 4 together, then again the rest makes an estimate of this, and so on. And you can test all these things. And therefore, we can do this estimation and use all the methods we use for the MAC converse. So in principle, if you look at the situation we have when we do the cut, it's comparable to the situation that we have for the MAC. And putting all this together, we get these inequalities here. And of course, some of them are redundant, so we don't need them. But in principle, this is the rate region what we get. This is the CIC, and you see we take the union over PXI and XY. And the things that we get from some of this inequality, some redundant ones, we also have the same phenomenon for the MAC. So we know that this is somehow an outer bound of the interference channel.